So this chapter is about linear regression methods. So just as before, we're going to assume that we have some variable x, which is going to be in Rp, and this is our independent variable, we're going to call it now. Well, in this chapter, we're also going to assume we've got a response variable y, which, to begin with, in this first video, I'm just going to assume it's a scalar. This is a response variable. And the assumption in this chapter is that the relationship between y and x is linear. In particular, we assume in linear models that the expected value of y is of the form x transposed beta, where beta here is a parameter vector in Rp. So we're going to look at a variety of methods here for estimating beta. We'll start with ordinary least squares, which most of you, if not all of you, will have seen before, I hope. And then we'll talk about some extensions to ordinary least squares, known as principal component regression, ridge regression. And finally, we'll talk about what happens when our response variable y isn't a scalar, but is itself a vector. What can we do? So let's start by assuming we have n observations. The observations come in pairs of the independent variable x and the response variable y. So we get x1 and y1, x2 and y2, up to xn and yn. Now the notation we'll use is that we're going to write our linear model in the form y is x beta plus an error term epsilon. And what we've done here is we've stacked all the y variables, all the responses, into a column vector, y1 down to yn. Then we've stacked the x's into what's often called a design matrix. So the first row is x1 transposed, the second row is x2 transposed, down to xn transposed. Then we've got our parameter vector, that's beta1 down to beta p, plus we have a vector of errors, epsilon1, epsilon2, down to epsilon n. Okay, so x here is an n by p matrix, beta is a p by 1 vector, epsilon is an n by 1 vector, and y is an n by 1 vector. So to make the presentation just a bit cleaner, we're going to assume that y bar is 0. Okay, so y bar is 1 over n, the sum of the yi's. So we've centered the data y, and that we have column centered the x's, so that hx equals x. Okay, i.e. x has been column centered. Okay. So if we think about what this model is, if we go back up here, if I was to spell this out here, this would be beta 1 x1 plus beta 2 x2 plus to beta p xp. Okay, so that's writing it out as a sum of scalars. This is in vector form. Now with this column centering, we can think of this model. Suppose it hadn't been column centered. Suppose y bar wasn't 0. We can think of this as a model for yi minus y bar is beta 1 times xi1 minus x bar 1 plus beta 2 xi2 minus x bar 2 plus dot 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 plus beta p xip minus x bar p plus an error term epsilon I. Okay, so where xi here is the mean of column 1 of x. So if we were to multiply all this out, then we'd get that this is yi is some constant plus beta 1 xi1 plus dot 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 to beta p xip plus epsilon I, where this constant is the sum of all the means kind of collected together. So it'd be y bar minus beta 1 x1 bar minus beta p xp bar. Okay, so we're just going to make life simpler, and we're going to assume that we've column centered everything, so all of these terms are 0. Okay, so we don't need a constant here. But if we hadn't column centered it, all that would happen is we'd have an intercept in the model that we'd also have to estimate. But we have to treat the intercept a bit differently in the methods I'm going to discuss later, and so it's just cleaner for me to remove it all, and so we're going to assume that we've been column centered and that the y bar is 0. And the software we use, the packages we'll use in R, will do all this for us, okay, so we don't need to worry about this. Now when we do this, we normally make a number of assumptions. So we typically assume, one, that the expected values of the errors is all 0. Yeah, the 0 mean. If they're not 0 mean, we need, well, there will be because we've column centered everything here. But if they're not, we just have an intercept to pick it up. So we're going to assume that the 0 mean. Then we assume that they are uncorrelated. So the correlation or the covariance between epsilon I and epsilon j is 0. I not equal to j. So that uncorrelated, 0 mean. And the final assumption is that they are homoscedastic, so that says that the variance of epsilon I is just sigma squared. Okay, so the constant variance, homoscedastic. Okay, so in linear models, we always make these 3 assumptions. Now, sometimes we also make an additional assumption. We sometimes also assume that epsilon I has a normal distribution with mean 0 variance sigma squared. Okay, so if you think about it, this fourth assumption has these first 3 baked in. If you like, you've got 0 mean, sigma squared, uncorrelated, but it also tells you the distribution. So we sometimes also make this additional assumption, and that allows us to do statistics with things. Okay, but we don't need it for what we're doing in this module, in that we're just going to be looking at parameter estimation. We're not going to do any statistical tests or anything like that. So how do we estimate the parameters beta? Well, one way is to minimize the sum of squared errors. So we choose beta hat as the value of beta that minimizes the sum of squared errors. So the sum of squared errors can be written as the difference between y and minus x beta with the 2 norms squared. Or if you want to spell this out, it's the value of beta that minimizes the difference between yi and minus xi transpose beta squared. I equals 1 to n. So this, written it as a norm here, is just a way, shorthand way of writing this sum of squared errors. Well, how do we find this? So I'm going to put a subscript here for OLS, ordinary least squares. So this is the ordinary least squares in that it minimizes the sum of squared errors. Well, y minus x beta squared, the norm of, is y minus x beta transposed y minus x beta. Let's expand this out. This gives us y transposed y minus beta transposed x transposed y minus y transposed x beta plus beta transposed x beta. Now these two terms are scalars in here, so this is just the same as y transposed y minus 2 lots of beta transposed x transposed y. So if I differentiate here, so if I do d by d beta of y minus x beta squared, well, if I differentiate this first term, I'm just going to get 0. If I differentiate this, I'm going to get minus 2 x transposed y. Differentiate this, I'm going to get 2 x transposed x beta. So setting the derivative equal to 0, which it will be at a minimum, okay, gives us what's called the normal equations, which is that if I cancel 2, minus x transpose y plus x transpose x, beta is 0. So if we rearrange this, we'd get x transpose x beta equals x transpose y. And if the inverse of x transpose x exists, we could write the solution as ordinarily squared estimator beta hat sine OLS is x transpose x inverse x transpose y. That's assuming x transpose x inverse exists. And we'll talk later about what to do if it doesn't exist. Okay, so this is the least squares estimator of beta, which you'll have probably seen tens of times before, okay, in previous modules. Yeah, the standard way of fitting linear models, least squares estimation. The only bit of jargon we need, and there's lots of jargon that comes with it here, but we'll talk about the fitted values. So the fitted values are y hat, and that is just x beta hat. Okay, so it's the predicted value of the y's using the estimated beta. So these are fitted values. So just a quick word on the geometric interpretation here. Just note that x beta is a point in the column space of x. Yeah, it's just a linear combination of the columns of x. And what ordinary least squares regression does is try to minimize, therefore, the distance between y and let's call it y prime squared, okay, where y prime is in the column space of x. This is another way of thinking about what linear regression is doing. It is finding a point in the column space of x that is close, or as close as possible, to the original data y. Well, this, you'll note, is just the definition of orthogonal projection. Yeah, this is what orthogonal projection does that we saw in chapter 2. Yeah, find the vector that is closest according to the L2 norm in some subspace. So we want to project y onto the column space of x, and by the proposition we saw before, which is proposition 2.5, okay, we know that the projection matrix is given by x transposed x inverse x transposed. Okay, so if we compute what this is, the projection of y hat, well, the theorem tells us it should be x transposed x inverse x transposed y. Okay, and that is exactly what we found here. Okay. So if we substitute in beta LOS here, we get this is x transposed x inverse x transposed y. Yeah, if I put this in here. So we've got two different ways of thinking about ordinary least squares. And a useful way of thinking it as the projection of y onto the column space of x. Now, we've column centered x here, so let's write down its singular value position, singular value decomposition. Let's suppose x could be written as u sigma v transposed. Well, in that case, we get that beta hat OLS, we said it was x transposed x inverse x transposed y. So let's substitute in the singular value decomposition. So if I transpose it, I'm going to get V sigma U transposed, that's my X transposed, times X, that's U sigma V transposed, all inversed, times X transposed, that is V sigma U transposed times Y. So U transposed U here is just the identity. By definition, use a partially orthogonal matrix. So we get, this is V sigma squared V transposed inverse, V sigma U transposed Y. Well, we know how to take the inverse of a matrix like this. We just take the inverse of the diagonal elements in sigma squared. So this is V sigma minus 2 V transposed times V sigma U transposed Y. So this is also the identity. And tidying up a little, we get that this is V sigma to the minus 2 times sigma, so sigma inverse times U transposed times Y. Now, this we might recognize. This was the generalized inverse of X, which we found when we did the SVD in chapter 3. Okay. This isn't really a surprise, right? We just discussed this briefly then. We've got the system Y is X beta plus an error. So it's not a surprise that a good estimate of beta is X generalized inverse Y. Yeah, and we discussed that in some of the exercises we did. But just to give you that, this is another way of writing out linear regression, and it's going to be useful when we talk about principal component regression. So let's think about the fitted values again. So the fitted values, remember, were X times beta hat. So we get, if we put in X, that was U sigma V transposed. Substitute beta hat, that was V sigma inverse U transposed Y. So this simplifies to U transposed Y, which we can write as the sum of UI transposed Y. I equals 1 up to P. So another way to think about this is that, again, OLS, ordinal least squares regression, projects Y onto U, okay? The left singular vectors. Yeah, we know they're orthogonal, so we don't need the U transposed U inverse anymore. They're orthonormal vectors. Okay? So ordinal least squares is projecting Y onto the left singular vectors of X. Now, is that the same projection as we had before? We had it projection onto the columns of X before. Well, we said when we introduced the SVD that U1 up to UP are an orthonormal basis for the column space of X. Yeah, so it's exactly the same as we found. We said we can think about linear regression as being a projection onto the column space of X or a projection onto the left singular vectors of X. It's the same thing. Yeah. So this just gives us a nice way of thinking about what linear regression is doing. So just one final point then is that sometimes we said if we had assumption 4 that the epsilon I were normally distributed with mean zero and variance sigma squared. Well, what would we do in this case? Well, then we might choose not to do least squares, but instead to do maximum likelihood estimation. Okay. So if we write the vector epsilon, what we've said, this is equivalent to saying that the vector epsilon is multivariate normal at dimension n with 0 for its means, and its variance matrix is just sigma squared times the n by n identity matrix. So the log likelihood of beta and sigma squared, well, that's log likelihood of beta and sigma squared. It's just exactly the log likelihood of the multivariate normal distribution here. So we're going to get minus n over 2 log sigma squared minus n over 2 log 2 pi for the normalizing constant. And then we get 1 over 2 sigma squared y minus x beta transposed y minus x beta. So, what can we see? Well, first of all, if we minimize, we do maximum likelihood, so let's maximize with respect to beta, the log likelihood, that's equivalent to minimizing with respect to beta, y minus x beta transposed y minus x beta. And so I think that's easy to see. Maximizing this term with respect to beta is just equivalent to minimizing this term, and there's no beta here, so I've got a minus sign here, so swapping that to a plus, it's saying it's maximizing. Okay, so the maximum likelihood estimator of beta hat maximum likelihood is the same as the ordinal least squares estimator. If we have normal errors, they're just the same. Okay, so there's a quick reminder that to do this in R, you use the LM command in R to fit linear regression. So there's an example of doing it with the iris data, okay, but you'll all have seen this before, so I'm going to leave you to figure that out for yourselves. Okay, the LM command can be used to fit linear models.